Hello, my name is Vlad. In the last video, Bamlik has talked about the CDL, MATLAB CDL channel model and how it can be utilized to run 5G simulation and extract KPIs in order to do hardware design. In this video, we'll be talking about the PyAEDT HFSS workflow and all of the limitations of the CDL channel that can be rectified in this workflow. So here on the right, you see the MATLAB CDL channel workflow. On the left, you see the PyAEDT workflow with HFSS. So this workflow starts with importing the city, the ray tracing environment, and here we're going to be demonstrating everything on the example of the design of the cell phone antennas. So here, the first thing is to import the ray tracing environment. Then you want to simulate the antennas on HFSS and find the installed antenna patterns, which you're going to be installing in the hybrid HFSS SBR ray tracing environment. Then you'll create the multi-port wireless channel model, and you're going to extract the KPIs, um, such as diversity gain, capacity, throughput, everything that you need. So to begin with, we have the city download from OpenStreetMaps. So in this example, we're going to be using Cupertino, and in order to do that, you need to obtain the STL files for buildings, roads, and terrain, all obtainable from the OpenStreetMaps. And here you see the HFSS model tree with the boundaries for buildings, roads, and terrain, to which you can assign different material properties. So assigning material properties is simple and everything done automatically in PyAEDT using scripting. So as here you see the picture of the roads, and for roads we use concrete with infinite layer concrete, and other parts of the city like terrain and buildings you can use other materials, asphalt for example, or concrete as well, or any other material you want. So here's a complete city, and then you see the Model 3 layout with layered impedance. So you have buildings, you have roads and terrain. Each of them are assigned layered impedance sheets in HFSS. So second part is to simulate antennas on HFSS. So we have two types of antennas. We have the UE antennas, and we have the base station G Node B antennas. So starting with the UE antennas, in this example, we have a cell phone with two antenna user equipment. The two antennas are orthogonally polarized. They're designed for Wi-Fi sub-6. So here you see the HFSS CAD model of the cell phone. So the two UE design, the first antenna is on top, is horizontally polarized antenna at 2.46 gigahertz. So here you see the S parameter plot, which demonstrate that it's matched properly at 2.46 gigahertz. So the second antenna is at 3.16 gigahertz, and again, it's vertically polarized and is matched at 3.16 gigahertz. So now, here are the different components you have in your HFSS design. So for example, battery can be assigned the PEC material. You have a substrate on which the cell phone is mounted and the antennas are mounted. And then you have a glass on top of the cell phone. And now we have a G Node B. In this case, we use a wideband array designed for 1 to 5 gigahertz, so it resonates at a very large band. So there is 16 antenna elements here. It's a planar wideband connected slot array. So now our goal is to install the antenna patterns into the environment. In this example, you have 140 UE antennas, dual band antennas, two antennas per cell phone, and then you have a G Node B. We place it in the corner in this part of the Cupertino. So here's the big blob is the G Node B, and then the small blobs are the 140 UE antennas, each having UEs, cell phones, each having two antennas with two different polarizations. So here's the model tree. So just demonstrating that in PyAEDT and in HFSS, you can have all the three projects together. So you have the Cupertino SBR Plus project, which is the ray tracing project. You have the cell phone MIMO antenna project. And then you have the planar array, which is a wideband slot array project, all in one place. Now you have to use the simulated antennas as excitations in the SBR. So in total, you would have 16 excitations for the 16 until elements in the G node B, and you'd have 2 excitations per cell phone antenna, all in the SBR plus. When your goal is to run the hybrid SBR ray tracing simulations, you have different options. Either you want to do the far field simulation or near field simulation, depending on the accuracy that you would need. For example, in the installed situations like like an antenna on a car or on a human hand or head, you might want to use a near field setup, which gives you more accuracy. In this case, we're just going to use a far field setup. You can also use advanced diffraction methods like creeping waves, physical theory of diffraction, uniform theory of diffraction to improve accuracy, and in other videos we'll demonstrate in which cases that can be extremely important. Then your next step is to create a multi-port wireless channel model in which the ray tracing simulation comes here as a middle block, and then you can have matching networks on the transmitter and the receiver side. You have the coupling, you have the noise correlation and different noise sources from the environment and from the amplifiers, and you include other things like match networks, amplifiers, filters. Then you extract the wireless KPIs. So what we do is we provide the channel models, we extract the wireless KPIs for the design. Um, so here you can have different KPIs, like for example, mutual information with throughput under different receiver processing schemes. For example, for MIMO, you can have linear processing schemes like MRC, MMC, zero forcing. You can have nonlinear processing or optimal processing schemes like MMC SIC receiver or uh, sphere decoding, so on. You might want to look at the diversity multiplexing trade-off or how much spatial multiplexing you can do by decomposing your channel in the angular domain. Or you might want to look at the block error probability as a function of block length to understand to understand better the length of the code that you might need. So thank you for listening and being with us.